Welcome to the fourth video of signals and systems. So we have been classifying signals on different grounds. We did classification based on the dependent variable time. Then we classified on the basis of periodicity as periodic and non-periodic. Then again based on the symmetry. And we also had a brief classification about the deterministic and the random signal. There's one more classification. Actually, it's not classification per se, but it is often that we are interested in the energy and the power content of our signals. And accordingly, we then tend to classify signals either as energy signal or as power signal. So we do a brief mathematical analysis. We will derive the relationship. It's a kind of a generalized thing that will help us to determine the energy content and the power content of a signal. Then once we have defined that, we will classify the signals accordingly. So we're talking about signals, and we are in the electrical and the electronics domain is our domain. So whenever we talk of signals, there are in these domains there are two quantities that's associated with the signal as voltage and current. Maybe a voltage signal, maybe a current signal. So if I consider a voltage, it is an instantaneous variable v of t. It's a voltage signal, instantaneous voltage signal, which is developed across some resistor, say R. Fine. And since there is voltage, it will produce a flow of current, and let that flow of current have an instantaneous value of I of t. Fine. Then there is resistance. Resistance is a power dissipating element. Voltage across the resistance, current flowing through the resistance, so some power will be dissipated. So let the instantaneous power dissipated in this resistor, let us denote that by P of t. That the instantaneous power in the resistor, it will be defined as, it is a basic relation that you have from your basic electrical engineering. It is, if you express it in terms of voltage, so it will be the instantaneous value of voltage squared divided by the resistance. Or equivalently, you can also express the power, instantaneous power dissipated as I square R. Right? These are two equivalent relations. But if I assume that the resistance that we are assuming here, it has a unit value, means it is 1 ohm resistance, then in both the cases the power, instantaneous power dissipated, it will be V square T I square T. So it will be directly related to the square of the instantaneous voltage or current. So if I generalize this thing, instead of talking about in terms of voltage and currents, if I talk about similarly the mathematical model of signal that we have used, I can kind of generalize that P of t is equivalent to x square t. That is the instantaneous power in a signal, whether you express it in terms of voltage or currents for a unit resistance, it will always be the square of the value of the signal at that instant. Right? Now we're not normally interested in the instantaneous power, so what we are interested is either in the total energy or the average power. And if I have to find the total energy, so let me just continue with the analysis here. So the total energy of this signal, which we have generalized now as x of t, it may be either voltage, it may be either current. It is then given as, that is E will be given as limit as time period t tends to infinity from minus t by 2 x square t dt. Yeah, you can directly say, instead of you can proceed to limit, so I can say it is the integral from minus infinity to plus infinity x square t dt. That will be the total energy content in this signal. Fine. So let's call it 1. Then another quantity we are interested is, it is actually derived from the energy. It's known as the average bar of this signal x of t, and it will be given by capital P. It is again limits t tends to infinity 1 upon t, that's time period, from minus t by 2 to t by 2 x square t dt. Fine. Let's call it 2. So we have an expression for the total energy content in this signal, and we have an expression for the average bar of the signal. Now same thing, it will be reflected to the discrete time case. Fine. So if it is a, I'm using a different color here, that in case of a discrete time signal where we don't have a continuous dependent variable, we have discrete time interval, just samples of this signal. So in case of a discrete time signal, which we denote as x of n, the relations will be the total energy it will be given. We won't be having the integral, we'll be having summation from n is equal to minus infinity plus infinity x square n. Fine, let's call it 3, which means it will sum up all the samples from minus infinity to plus infinity. And then average bar, it will be given by again limits n tends to infinity 1 upon 2n. 2n will be the total number of samples, then n runs from minus n to n x square n. Fine. And now that we have these relations, we have the relation how we can quantify the total energy content in this signal. We can also quantify the average bar that exists in the signal, both in the continuous time and the discrete time domain. So then we kind of classify signal on these two expressions. So we define a signal. So let me write it down here. A signal is referred to as an energy signal if it has a finite energy. That is, if I put it mathematically, if and only if the total energy of this signal is finite. So mathematically it means it should be something like this. Energy should be within the limits 0 and infinity. It cannot be infinite. And if your signal satisfies this property, we call this as an energy signal. Similarly, a signal will be called a bar signal if and only if its average bar is finite. That means your bar signal will satisfy this. Fine. We actually won't be using this classification so much, but it's always there's always a tendency to know what is the energy content within the signal. Yeah, what is the average bar for the signal that is being analyzed, especially in communications. When you go to the next class, you will have a course on communication, so we're always interested in that. A particular frequency, how much power that particular frequency has, something called spectral power density. Inshallah, you will learn about those things. But this is the brief analysis that tells us how to quantify these two contents. And occasionally we kind of then define the signals on the basis of these quantities. As energy signal if it has finite total energy, and as a power signal if it has a finite average power. Fine. uh, then another, if I combine the property of periodicity, so the relations get slightly modified. So let me just put it down here that the average power, if you have a periodic signal, periodicity we defined in the previous lecture, in the previous video. So if you have a periodic signal, then you don't need to calculate it for over an entire range from minus infinity to plus infinity. I mean, this limit is not necessary then, because it's a periodic signal. So periodic signal have a special property that you can calculate over one period. Fine. T is a time period, x square t, so you can get this average power. And for the discrete time case, you can very well use this kind of a relationship, x square n. Right. So these are kind of modifications that if your signal is periodic, then you don't need to calculate the average power in both continuous and discrete time cases for the infinite, for all the time. You can always calculate it over one period. Fine. And another thing that you'll have to remember, again, this is something you will learn in the next class, but I'm just, for the sake of remembrance, always remember that a signal cannot be both an energy signal and a power signal. Hence the classification, because if there were signals that satisfied both the relations, that had finite total energy and finite average power, then there would, and then this classification made no sense. Right? So there's a generalization that if your signal is an energy signal, it cannot be a power signal, and the other way around, if it is a power signal, if its average power is finite, then it cannot be an energy signal. Okay, so this was the yet another classification. We will do some numerical problems in the tutorial session, which will be a live session, wherein we will be taking some test signals, simple signals, and we will be interested in the energy content and the average power that the signal has. Right. So that is about, this is about the classification. Next video we will start with the basic operations that can be performed on the signal. Thanks.